Hello everybody, welcome to yet another video by JFB, and in this video we'll be looking at the NAND gate. So we're still in the topic of logic gates, but we're going to move on to a more complex type of logic gates, as the NAND gate is actually a combination of two of the basic logic gates. If you don't remember the basic logic gates, here's a recap. So we have the NOT gate, OR gate, and the AND gate. I strongly advise you to watch the previous videos which I made, as I explained all these types of logic gates in a more friendlier way and in a more deeper way. The NOT gate can be represented by this diagram, a triangle there and a circle there, and it only takes in one input and produces one output. As for the OR gate, it can be represented like this, simply being a logic gate which takes in two inputs and produces one output. And the AND gate can be represented like this, very similar to the OR gate, but don't get confused. The OR gate has a curvature at its back end. As for the AND gate, it's straight. So we have that two inputs also and produces one output. For the NOT gate to produce an output of 1, it has to take an input of 0 and it will produce an output of 1. If you give it an input of 1, it will produce an output of 0. As for the OR gate, it's quite different. For it to produce an output of 1, it has to take on any of its input an input of 1. So 1, and maybe this can be 0 or 1, but maybe it's 0, and it will produce an output of 1. If both of these were like 1 1, it will still produce an output of 1, as it only needs one input of 1 in order to produce an output of 1. For the AND gate, it's different also. For it to produce an output of 1, it has to take in two inputs of 1. So 1 1, that's the only time the AND gate will produce an output of 1. Now the NAND gate is actually a combination of two of these basic logic gates. The combination consists of the NOT gate and the AND gate. Actually, you can even hear it from its derivatives, NAND. So an AND somewhere there and an N, which signifies like a NOT or like that. So it's just NOT plus AND, nothing else. How can this be achieved? We can actually do this in a very simple way, by feeding the output of the AND gate into the input of the NOT gate. What do I mean? So let me draw this. Let me draw an AND gate here for you to see what I mean. So here's an AND gate which is taking in some inputs there. Then we can feed the output of this AND gate into the NOT gate. So we can connect a NOT gate there and it will produce an output. So how is this working? Well, the AND gate will take in some inputs here. It will take in maybe a 1 1. And if the AND gate takes in an input of 1 1, it will produce an output of 1 here. This output of 1 will be the same one which will be given to the NOT gate. And what will happen to the NOT gate? It will produce an output of 0, as when the NOT gate takes in an input of 1, it always produces an output of 0. Simple as that. So if you don't get the interpretation, just think of it like this. Whatever the AND gate gives me is what I will give the NOT gate, as the NOT gate only requires one input and the AND gate is probably producing one output. The NAND gate actually has a representation on its own. It has a diagram which depicts it, drawing circuit diagrams and all that. So the NAND gate is depicted by drawing an AND gate. Then in front here, you just place a circle. That's all. Where is this circle coming from? From the NOT gate. So a circle there, then an input line and an input line. So this is the NAND gate representation. You can Google it if you want. That's how the NAND gate is represented in all circuit diagrams. A simple AND gate and the circle of the NOT gate. Now let's draw a truth table in order for us to see how this NAND gate is actually working. And if you don't remember or you forgot, which is understandable as we are all human beings, the truth table is a table in which we can track the inputs which were given to a logic gate, and we can also track the outputs of that particular logic gate. That's all there is. It's so simple. We just track the inputs and the outputs. There's actually a rule in determining what kind of inputs or the input pairs a logic gate can get, and that is 2 to the power x. What do I mean by this 2 to the power x? Look at this NOT. What input set or what kind of inputs can it get? So it only takes in one input. The x is actually representing the inputs that logic can get. So it takes in one input, and that will be 2 to the power 1, and which will go to 2. So this 2 is representing that this NOT gate can take a 0 or it can take 1. It can only take two distinct inputs. As for the OR gate or AND gate, which has two inputs, we say 2 to the power 2, which is equal to 4. So there are more combinations which we can add onto this OR gate. We can add a 0 0, or we can add 1 0. And by the way, we have flipped the sides. We have only flipped the sides. So don't be confused. Don't think that 0 and 1 are and 1 and 0 are the same. They're actually different, because this input is going on a different line and this input is also going on a different line. So like that. Let me draw a truth table for the NAND gate and show you what I mean by this in a deeper explanation. I forgot to state this in my previous videos, but don't worry, it's not even a big deal. Just try to follow along. Coming back to the NAND gate diagram, we can label these inputs and outputs. So we can label this input here as A and this input here as B. The output can be labeled as a C. I normally pick this conversion because it's very simple. So, and remember, when we say 2 to the power x, that means it takes in two inputs, and that can be represented as 2 to the power 2, which is equal to 4. So our truth table will have 4 rows. And why do we have 4 rows? Because the input set has 4 pairs of input. That means it can either be 0 0, it can either be 1 0, 0 1. And by the way, these are different. A and B are not the same. So when A has 1 and B has 0, it's not the same when B has 0 and A has 1. We will see this further in logic circuits, whereby we actually combine logic gates to form some kind of a circuit. Then we have 1 1. So it has 4 input pairs. Now let's do a truth table with all these figures inside and see what the NAND gate is producing and how we can compare it to other logic gates. So you draw A, B, C, like that. Then this truth table should have 4 rows. So 1 row, 2 rows, 3 rows, and 4 rows. Simple. So now we can start entering these input sets. So the first input set, we can say, what if the A input was 0, it takes no voltage or no current, and the B input takes no voltage and no current? What do you think the output at C will be? This is not an AND gate whereby we can simply use some rules and that. This is actually different. So if you get stuck, like I am stuck here, you can think of it, what's the output of the AND gate? And to make things simpler, we can actually separate NAND gate into what it's actually made of, into simpler terms, like that. So simply a NAND gate and a NOT gate. So now let's think. So A is 0, this will be at A, and this will be B, and our C will be here, not here. So A is 0 and B is 0. What do you think the output of the AND gate will be? The output of the AND gate will be 0. When we feed this 0 into the NOT gate, what do you think its output will be? It will be a 1. Simple as that. Now let's change the values. So we have an input line of 1 there on A, and an input line or an input of 0 on B. What do you think will happen? So 1 there, 0 here. So we have 1 0 there. What do you think the output will be here? The output here, as for the AND gate, these values are not the same. They're not all ones. So here it will be a 0 again. When we feed this 0 into the NOT gate, it will be another 1. Let's go on to the other input set. So we have 0 there on the A and 1 on the B. What do you think the output will be for this? So we have 0 here and 1 there. We feed both of these values into the NOT gate. This will also produce a value of 0, as the AND gate needs 2 1s for it to give out an output of 1. So 0 there. Then we feed the 0 into the NOT gate. The NOT gate will produce an output of 1. Again, anytime the NOT gate is given 0, it produces an output of 1. What about when we have 1 1 here? So 1 1 will be different. 1 1 on the AND gate will produce an output of 1 here. This one will be the one which will be fed into the NOT gate, because whenever the NOT gate takes in an input of 1, it produces a 0. And there we have it. That's the truth table for the NAND gate, just like that. And again, let me repeat this. If you forget how the NAND gate is working and its truth table, don't worry and don't stress. Just break it down into its simpler components and work it out from there. You can actually form a general rule from this truth table. Check out. Every time there's 0 0 or 1 0 or 0 1, or when there are bad terms for the AND gate, that's when the output of the NAND gate will be 1. And what do I mean by that? Just try to think of the numbers or input sets which make the AND gate fail. Every time the AND gate is failing, that's when the NAND gate is producing an output of 1. That's all there is to it. I'm sorry if this was confusing and all that, but try to master all these values. You have to learn all this in order for you to understand computer science better and to really gain out some benefits or appreciate the science. This is not useless actually. This is something that will be used in programming in real life, because the NAND gate and how it works will be used maybe to create conditionals especially. You hear this word in all types of programming courses you do, whether you're programming in C, Python, Java. If you don't know what these things are, don't worry, that's what you use to write your code from. So to end this video, I would just like to say thank you. Please leave a like, share and subscribe.